Now, already this is a high school stuff. Like you already, all of you know, like galvanic cell and electrolytic cell, right? So just again, just to recap it. Okay. So like a galvanic cell is something like. So let us just take an example. I think that will be better. And this is the Daniel cell, right? Okay, so what is a galvanic cell? Galvanic cell is basically louder. There are two kinds of cell, right? Galvanic cell and electrolytic cell. Now, what is a galvanic cell? Is for basically producing electricity, right? Now, the thing is that if I just connect these two, of course you know that there's a half cell, right? And I have to basically, to get the total cell potential, I have to basically take E right minus E left. There is a convention, right? But the thing here is that, as you can see, that I have oxidation here, right? So wherever I have oxidation, that electrode I denote as anode, right? So and then what will happen? This zinc, okay, so suppose this is zinc metal, and it is coming to the solution, okay, the zinc 2 plus ions, leaving the electrons here. So this becomes a negative electrode, right? And this becomes a positive electrode, so that the electron actually flows from like zinc electrode to copper electrode, okay. But if I actually reverse the concept in the sense that, okay, I am writing the same thing, okay. Here we have a different electrode potential. Now in this case, actually what happens, like as you can see, like what is happening, water is getting oxidized here, right? And the electrons are deposited here. Now wherever I have oxidation, that I will call as always anode. Okay. So valve for valve. Okay. But here the only difference is that from the galvanic cell with the electrolytic cell is that in galvanic cell my negative electrode here is the anode. Whereas here actually, as you can see, here also I have the which way? I have the copper and the zinc. Just 1 minute. I have so water is getting oxidized, so yeah, the electrons will flow. But in this convention, what happens is that we always write plus and minus for anode and cathode. Okay. So anode always you keep in mind that irrespective of the type of the cell, whether it is a galvanic cell or an electrolytic cell, okay, it will be always that electrode that actually where actually oxidation happens. Okay. And cathode is basically the other electrode. Okay. Now, as you can see that I can actually use, suppose for example, what is electrolysis? Okay. Now, all of you know all these things. So, electrolysis means suppose I will like supply electricity, okay, and let something deposit on something, right? Suppose I want copper plating, okay. Which cell I should use? Galvanic cell or an electrolytic cell? Actually, I can use anyone. If I use a galvanic cell, okay, where actually this reaction is spontaneous, right? I'll actually use an electrode along with copper, where actually copper will be deposited, okay. Or I could have actually used a potential external bias, okay, to make that opposite reaction happens, okay. So that way also I can do electroplating of copper, okay. So electrolysis does not always mean that you have to do electrolytically itself, okay. You can also do it in a galvanic cell. It only depends on the difference in the potential. Now this is the standard thing which everybody starts with, right? The Danielson and other things. But the thing is, like, and this is a very like common thing. Common thing in the sense that usually we will always have two half reactions, right? Two half cells, and then we connect it. Okay. Now, which means actually we'll have basically two electrodes to begin with, right? And then there is an electrolytic solution. That is the only thing, right? Now the thing is, like, what could be these electrodes? All of you know that most of the cases, the way I have shown here, is basically the metallic electrodes, right? Like platinum, hydrogen, all these things, right? So like electrodes can be of metallic in nature. Okay. They can be also liquid metal. For example, like anyone, liquid metal, any amalgam, let's say mercury. Okay. So they can have actually liquid metal. Okay. Not only metal, you can also have semiconductors. Okay, like ITO, Indian tin oxide, right? Let's say mercury. Something like that. Okay. And similarly for the electrolytes. Okay. I'll also have, like, usually it is aqueous solution, like with water and some soluble salt. Okay. Like it can be like NaCl or something, potassium chloride, whatever. Okay, we'll come to examples actually. It can be also, let's say, conducting polymers also. Like in solar cells, so we never use actually any solid liquid solution because the volume will be large. Okay. So any conducting polymer. It can also be solid electrolyte. Okay. Anyone? Solid electrolyte? Like all your mobile phone batteries, right? And those are dependent on solid electrolytes. Okay. Lithium ion batteries, all these things, right? But actually it happens basically the lithium ion moves in and out, okay, of a like intercalated structure. Okay. And then per cycle, basically this intercalated structure, the composition and other things, they get degraded. Okay, that's why mobile phone battery also has lifetime. And the entire like current technology is based on that. Okay. But there are also sodium-based batteries which are being developed. Okay. So an example is sodium alumina. Okay. Now, the thing is, okay, I have basically electrodes, I have electrolytes. Okay, and the overall function of a cell will depend on basically how the electrodes and electrolytes are basically functioning. Okay. Now, what happens at the electrode and electrolyte is basically some electron transfer will happen, right? We know. Now, of course, within the electrode, okay, electron transfer is happening, but in the solution phase, what is happening? The ion transfer, right? So both are important, like electron transfer as well as the ion transfer. I should say not only electron, it is electron or hole. I mean the way you want to see, okay, electron and hole transfer. So electron and hole are actually mobile carriers for the electrodes as well as external circuit. Okay, we usually do not talk about that when we talk about electrochemistry, because we usually use like a standard definition like a copper wire is attached. Okay, okay, because copper wire has a perfect a particular standard resistivity. Okay, so do not focus on that part. Okay, what is the mobility of electrons? But definitely the mobility of electron matters at the interfaces, meaning like as I said that I have basically G and I have G2 plus here, right? So when the electron transfer takes place, okay, there of course it matters a lot, okay, and many like investment has been there, okay, in developing the surfaces and interfaces. So all this electrochemistry thing is actually very much an interfacial phenomenon, which we discussed, like surfaces and interfaces. But this is a surface electrochemistry now we are talking about. Okay. The very specific nature of the surfaces also matter. We'll see an example today. Okay. Second thing, the mobility of the electrolyte will also matter, right? Like how they are mobile, and we'll talk about it in like a later class. How basically I can connect the ionic mobility, okay, to something known as conductivity of ions and conductance number and all these things, right? Now these two things matter, of course. Now the question is how these two things are connected, okay? Or meaning basically when I am, all of you know that if I am actually having an electrode inside a solution, okay, there is always a potential difference, okay. Now the question is, okay, how we can actually quantify the potential difference, or what is the basic nature of the potential difference, okay. Now usually when we talk about electrode potential, okay, we usually write all these half-cell reactions, standard half-cell reactions, right, with respect to some standard electrode. And all of you know that standard electrodes can be of different types. The most like widely accepted one is the standard hydrogen electrode, right? Now there, just now there actually we have the electrode is actually platinum, right? And the way we always write it as I have platinum. Some textbooks actually write it as a vertical bar. Okay. Why? Because these bars basically represent the two phases. Okay. Because this is a gas phase and this is a solid phase. Okay. Now once I have a gas phase thing, okay, let's say I'm just writing platinum and hydrogen. How it will look like? So basically I have a platinum electrode. Okay. And of course, like it will be inside a glass where actually I have hydrogen gas. Okay. Now, as you can see, that I'm assuming that everyone knows Nernst equation. Okay. Now it will be when I am talking about platinum, right? I have to write basically a cell reaction where I will have a E0, okay, plus the concentration of the species. Right? Here the species is basically metal. Now, ideally, I cannot write concentration because we already talked about it. For electrolytes, particularly, we have to write in terms of activity. Okay. Now, if I replace it by activity, metals, pure metals always have activity equal to 1. We discussed it, right? Problem is here, hydrogen, right? It's a gas. So I have to use basically either fugacity or activity, some kind of concept. So by definition, okay, I always choose that this activity is basically equal to 1. Okay, because this cell, right, any cell will have a E0, standard thing, plus RTL and all these terms. Okay, but that terms I am actually making 0 for the standard definition. How to make it 0? Basically I am making it to be 1. Platinum I never write activity to be 1 because it's already a metal. Okay. And then of course I have what? Like the aqueous phase, I have basically H plus. Because the fundamental reaction is H plus getting reduced to H2. Right? So the H plus again I have to write an activity. Okay. So by default actually we choose the activity to be equal to 1. Okay. And of course I have to write it that it is in aqueous phase. Now this represents a cell diagram. Okay, a notation, a shorthand notation, where actually I am describing the half cell, okay, for the standard hydrogen electrode. Okay. And we take the standard potential of this cell to be equal to 0. Okay, and we measure everything with respect to that. Again, we usually do not use this thing. It's called actually standard hydrogen electrode or normal hydrogen electrode. Okay. But usually we do not use it because of practical purpose. You always have to keep the hydrogen activity to be equal to 1. You have to always pass hydrogen gas. Okay. So it's also not very much like portable, right? You have to basically transfer hydrogen gas. So for that actually we have alternate electrodes, which is known as, one is this calomel electrode, right? You know probably all these things. So, which is nothing but mercury mercurous chloride. Okay. In KCl, okay, but this KCl, okay, what is KCl? It's a potassium chloride aqueous solution. But then activity cannot be equal to 1 because it's a solution. Okay. So like so all we can say is that this KCl maximum we can take as a saturated solution. Okay. So instead of writing A equal to 1, we write it as a saturated aqueous solution. The potential of that, okay, with respect to the standard hydrogen electrode is something like 0.2424. Yeah, clear. So this is one of the practical electrodes. Okay. There is another practical electrode which is silver chloride electrode. And the potential is so when I say plus 197, it's good to write like versus standard hydrogen electrode. Okay, because you always measure the potential. Okay, how do you measure the potential? You always measure the electromotive force of a cell, right? And each cell has two half cells. You always measure the differences in the Gibbs energy, delta G, right? You are not measuring the absolute Gibbs energy. You cannot actually. So the delta G is the difference, and that's why you always talk about the differences. Okay, that delta G is, of course, you know that it is minus NFE. Okay, or I mean the standard state will be defined as minus NFE. So we'll review it, but not in this class. We'll just give you a very interesting introduction, alternative introduction to this. Now, suppose I have a like cell like this. Okay, I have suppose platinum. I mean these are basically the standard electrodes. Okay, this is known as, it's called saturated caliber electrode. Okay, the reason is basically I have a saturated solution. Okay, and similarly I have the silver electrode. Okay, all right. Now the question is, suppose I have what will be my arrangement, experimental arrangement. I'll have basically two electrodes. Okay, and I'll just basically dip it into the solution and I'll have an external circuit. Okay. Now think about it. I have, suppose, just think out only one thing, like I have process at a one particular electrode. Okay. So what I'm doing is that I dip the electrode. Okay. So I know that there is a potential developed. Okay. Now I will always keep in mind that the potential is developing only across the interface. Okay. So that's why interfaces are so important. Now I'm suppose applying some voltage to it. Okay, so what happens? So ideally, like when you talk about electron transfer, right? So the first thing which the way chemists think is that like I have electrolyte, okay, and this electrolyte has some molecule. It can be said ion also, okay, that zinc 2 plus or something, okay, and where basically all the electrons up to the HOMO are filled, okay, and there is a unoccupied orbit. Okay. Now what happens is that I have my metals potential, okay, somewhere here, okay, which I can change. How will you change it? Basically, I can choose a particular electrode, or actually I can take a particular electrode and apply potential. If I apply potential, I will basically tune the potential like this. Okay. And suppose an electrode means something like we always represent it by one electron. Why I am showing it as one electron? Because I am saying that it has a basically conduction band, where actually it can accept electrons as well as it can donate an electron. Okay, it's not really an one particular electron because it is basically a continuous band. It's a metal here. Okay, but the only point is that it can still accept or donate electrons. Okay. Now what can happen is that, like suppose if I can position my electrode here, okay, or if I scan the potential, okay, I can have an electron transfer from here to here, okay. Alternatively, as you can see, if I had the potential scanned here, okay, I could have an electron transfer from the solution to the electrode, okay, because it is still like vacant, okay. So meaning this is usually known as, so what is happening here, as you can see, the electron is leaving the electrode, okay. So it is kind of an anodic process, okay, versus this is a kind of cathodic process, okay. Now I will give you an overview. If I do this thing, Okay, suppose I have a fixed electrode and I'm just basically scanning this potential. Okay, what will happen? Okay, at what point like I will have how the current will flow. Okay, well, so basically all I'm trying to understand is that if I scan the potential external, okay, and tune basically the energy level of the, it's not energy level, it's basically the relative potential of the metal, okay, with respect to the solution, okay, so that I can facilitate this electron transfer or this electron transfer, something like that, okay. Then, of course, once the electron transfer happens, then the circuit gets completed, right? Then I will have a current flow, right? So all I'm looking at is basically if I scan the potential, how the current changes, okay. And I have a very let's say very like interesting setup here. Okay. What is that? Suppose I have something like some solution, okay, and I have just dipped platinum electrode here. Okay, this is not a standard hydrogen electrode. This is just a platinum metal. Okay, dipped in a solution. On the other side, I have suppose some electrode which is the silver chloride electrode. Okay, so it's basically how to, let me just first draw it. So I have basically a piece of a metal which is silver, okay, and outside I have silver chloride or silver bromide. Remember that when I write the AgCl or AgBr, okay, there also activity is by default 1 because this is also solid. Okay, it's insoluble. Yeah. And in the solution, suppose I should have what? I should have some kind of ion, right? And suppose I'm taking here, let's say, some bromide solution of some say activity. Okay. And then what I'm doing is that I'm basically connecting these two and I'm asking this question: how much is the potential drop between them? Okay. And I can have a power supply. You can also measure this in the current. Okay. So what I did is basically I have two electrodes. Okay, one side actually I have some standard half cell. Okay, and other side is just a metal. Okay, and it's also aqueous solution in the sense that it's bromide water. Say let's say KBr, whatever. Okay, and then what I'm doing is that I have placed a potentiometer between them. What is a potentiometer? Is basically I should have a parallel connection, right? And a potentiometer by definition should have infinite resistance, so that I mean practically no current flows to it within it. Okay, and then I have some kind of ammeter where I can actually look at the current flow, and I have a power supply where actually I can apply say positive voltage as well as a negative voltage. Okay, clear? This is my setup. So what I'm doing is that I'm basically scanning the potential, okay, and trying to see how the oxidation and reduction reaction as they are occurring, okay, how the current flow is happening. Okay. Now think about it, there are many things can happen. First of all, actually there is water. Okay. Now water can actually, like basically there will be a H plus and water kind of equilibrium. Okay. Like what I'm trying to say is that there will be some equilibrium like this. Right? So this reaction will happen at some point. Now every reaction, as I know, has basically an E0, right? What is basically the standard reduction potential. So when I'm scanning the potential, okay, when the potential actually reaches around the value of the potential corresponding to a particular reaction, then the reaction happens. Okay, it is basically the other way of thinking. However, just keep in mind this cell is a very special cell in the sense that on one hand, okay, I have a like thermodynamic equilibrium between say silver bromide, all these things. But here I don't have because I'm not bubbling any hydrogen. Again, it's just a metallic electrode. Okay, it's not actually in that sense are two half cells. Just one half cell is present. Okay, but we can still measure the potential. Okay. Now in this configuration, if I just attach if I just connect a voltmeter, okay, and if I just do not just turn it off, okay, say zero power supply or something like that, zero potential, okay, I might steal some residual current, okay, because there is could be a net potential difference that is acting and that is causing a current flow. So I might actually have to supply some current, okay, to stop, apply some voltage to stop that current, okay. So that voltage which is required to get a zero current, okay, is called actually zero current voltage, okay, or zero current potential, or more commonly as open circuit voltage, okay. So basically open circuit voltage corresponds to a voltage or potential, okay, where actually my current will be zero, okay. So it is not always necessary that the zero potential will give you the zero current, because always I'll have a residual potential difference. Okay. We'll see actually here open circuit voltage is slightly different, okay, and it has some alternative names. It's sometimes called zero current potential, or sometimes it is called rest potential. And the name basically is obvious, right? Why it is called zero current or the rest potential. Okay. Now just think about it. What is happening? So I have basically this thing when I am actually applying voltage. Okay. So what can happen is that I have the H plus ions that can go to hydrogen. Okay. Or I can also have bromide here. So I can also have another electrode reaction, which is something like, if I write it in a reduction way, okay, I have to write it in this way. So this reaction can also happen. Clear? Okay. Now whenever these reactions are happening, these are happening at which electrode? Platinum electrode. Right? And there will be always a counter reaction in the other electrode. Okay. Now usually this electrode, as we said, that this is, we call it as a reference electrode. Okay, like standard hydrogen electrode, that's a reference electrode, right? Because I am measuring everything with reference to that, okay. Or say like this is also a standard electrode, okay. So silver bromide electrode that has a particular potential with respect to standard hydrogen electrode. This is called a secondary reference electrode. But what is the meaning of the reference? Okay, so this I am saying actually this is a reference electrode. Now think about it, what kind of reaction will happen in the reference electrode? The reference electrode I have basically silver bromide, right? So I will have silver, bromide is basically silver is oxidized here. So if I have one electron here, okay, so I'll have silver. So this will happen, okay. So when I have an oxidation there, I'll have a reduction here. When I have a reduction here, I'll have an oxidation here. It has to happen. Okay, only this thing cannot go undergo oxidation because the circuit won't be complete, right? You know that, right? But the interesting thing is that when this reaction is happening, okay, think about it. What is happening? Silver bromide is going to silver, okay, or the other way. Silver is going to silver bromide, okay. And then if I just write the Nernst equation for this half cell, okay, what will be the half cell's Nernst equation? I'll have a E0 half cell, okay, plus some RTLN reductant by a concentration of reductant, reduced species by oxidation species, okay, that way. But think about it, when I'm having this reaction, okay, silver bromide is going to silver, but both sides activity is equal to 1. It doesn't matter, like if the 10 molecules of silver bromide is giving me silver, it doesn't change, the activity is still 1 because both are solid. Only change can happen, the bromide ion will appear and disappear. But if I assume that the bromide I have excess concentration of bromide, that also doesn't change. So that part, the RTLN, that factor is basically essentially doesn't change. Okay, as I'm using this thing, okay, this reaction. So basically the reference electrode, okay, is not contributing too much change in the potential in this reaction. Its potential is not changing, it is still E0. Clear? Okay, it is actually contributing only the E0 but not the other part. Okay, so all the other part is now actually taken care of the platinum. So I actually don't need to actually consider what is happening in the other electrode, in the reference electrode. Okay, that's why the reference electrodes are chosen in such a way. Okay, usually a solid with reduced or the oxidized form, which is another solid. Okay, but of course you will have a mobile phase in the sense that you need an ion. Okay, but if I also use the ion in excess and assume that the ion's concentration is not changing much, okay, so that is also constant, then my like total electromotive force is also constant for the upside. Okay, that's why it is known that the reference electrodes are those electrodes where actually during the electrode reactions, okay, its own potential is not changing. Clear? Alright. Now think about it, suppose everything is happening in the platinum, okay, and then I am basically scanning the voltage, okay, I am basically applying power here. Now, usually, as I drew this thing, let me just draw it 1 second, okay. So like, usually the convention is something like I wrote this image, right? So like it's HOMO and it's LUMO, right? HOMO and LUMO of a species which is in solution. Okay. And then I have basically the electrode which, and there is an interface. And across the interface the electron transfer occurs, right? Now if I apply a negative bias, usually, okay, the potential or the energy level is basically gets elevated. Okay. And then I have a metal energy level which is much higher. Okay. So then actually I facilitate this process. Okay. On the other hand, if I just lower the potential, I can facilitate this process. So the idea is that usually the negative bias, okay, is shown in the top and the positive bias is shown in the bottom. Okay. Now when I write my x-axis, where basically I am scanning the voltage, okay, I usually write the positive voltage here and the negative voltage in this direction. It is the other way. That's the convention. Okay. Because actually it has a very direct analogy with this. Okay. And that's why usually we write the standard reduction potential convention. We never write the standard oxidation potential convention. Clear? Okay. So suppose I'm scanning the voltage and then what I will have, I will basically want to monitor what is the current. Okay, current flowing in the circuit. That is basically given by the SI ammeter and I am scanning the voltage. That's a simple experiment. Okay. And I can assume under this condition, all the reaction or all the potential changes happening at the platinum interface. Okay, because the other interface does not really participate. Okay, it's a standard electrode. Clear? Okay. Now what will be the curve or the nature of the curve, how it will look like? Plot it. Now think about it. Now when I am scanning, right, the voltage, I am going to say more negative side, okay, which means actually this side I am suppose scanning, okay. So this reaction can happen, okay. Now this reaction, okay, is happening with respect to what? With respect to platinum, okay. But we have already taken it to be kind of 0, right? But it will not occur exactly at the 0. Why? Because there is no hydrogen present. Okay. If hydrogen is present at one unit activity and then platinum is there, then that potential is basically 0. Okay, it will be slightly off from 0. Okay. So if I scan the potential, at some point I will see that all of a sudden the current will rise. Okay. At what point? That point where basically the potential will match the standard reduction potential of one of this. Clear? Okay. So I'll have a basically current like this, and I'll basically have a like shooter in the current. Okay, with a very small change in potential, which means that I have reached already that thing. Okay. So this thing actually basically marks the onset, okay, of this reduction. Okay. H plus reduction. Clear? Okay. So as you can see here, basically the H plus is getting reduced. Okay. Or in other sense, the electron is getting transferred into the solution, which makes sense because I have actually increased the metal's energy level. Okay. So the metal is basically supplying electron to the species in solution. What is the species in solution? H plus, protons. Protons are getting reduced. But it's an oxidation process basically, because actually the electrode surface wise it is a kind of oxidation process. Electrons are leaving. Okay. Now, similarly, if I actually reduce it, of course there will be a reduction process. Okay. Then I am actually scanning this thing. Okay. And then what will happen? Basically, it will nicely match. Okay. With maybe some other thing. In this case, actually, it will match this potential. Okay. And if it matches at some potential, it will again show a current. Okay. But this time the current will be in the other direction. Makes sense because actually you are reverse the direction of potential. Okay. And that will happen at something which is like, I'm not writing according to the scale, it is something like 1.00. And here actually I have something like this. Okay. And here I have onset of, if I call this as an onset, okay, so this is basically onset of Br minus oxidation. Okay. If I think it like this, it's a reduction process of bromine. Right? If I think in the reverse direction, it is basically Br minus oxidation. So onset of bromide oxidation. Okay, but H plus reduction, bromide oxidation on platinum surface. Okay, these are on platinum. The other reaction is also happening in other electrode, has to, right? But I don't care. I'm only focusing on the platinum surface thing. Fine. Now this is a very obvious thing, right? So this will be something like this. Okay, but there are a few things. What are the few things? Think about it. Okay. So this is basically the current, right? And as you can see that there is a range of potential. Okay. Where actually, even if I scan the potential, okay, I'm not basically getting any current. Okay, and all of a sudden it's, and as you can see that it basically starts rising. Okay. So what happens is that you can think in a very classical way, in the sense that I have electron and nuclei bound, right, in a metal, and then I'm applying a potential. So what it is doing is basically it is trying to make it polarizable, right? It's making it polarized. Now it will depend actually these atoms in the metals how polarizable they are. Okay. So like I'm actually applying voltage, and at some threshold voltage, the electron is actually ripped off. Okay, that is what is happening. Okay, so if the polarizability of the metal, okay, and exactly the opposite process is happening in this case. Okay, actually I'm trying to push one electron. Okay, and the electron cloud in the metal is basically opposing, but at some case actually the electron is going inside, right? So this range is basically describing me how polarizable is the metal. Okay, and we'll see it actually. So like the more the polarizability of the metal, okay, I'll have this range actually, I can broaden it. Okay, all right. Now think of a slightly different process, slightly different in the sense that I have the similar electrode, okay, but instead of like platinum, now I'm actually changing it to the mercury electrode. Okay. Let me actually write the Hofstadter reaction. Just for me. Yeah. So I'm only replacing this platinum by another just metal, which is just mercury. Okay, mercury amalgam thing. Okay. So what I have is, earlier I had this thing, platinum, and then what I should have? I should have basically H plus. Okay. There was no hydrogen. It's not a, again, standard hydrogen electrode. It's just a metal deep there. Okay. And then I had also in the same phase bromide. Okay. Let's say I made it as 1 mole. And then I had another interface which was AgBr. Okay, so this was my first experiment. Okay. Again, this is a proper half cell, but the other one is not a proper half cell. Okay. And second thing, as you can see that this is basically the liquid phase or the solution phase. Okay, so solution phase species usually we write as comma. Okay, but then again there is another interface which is the silver bromide, and then again there is was silver. Okay, now all I'm changing is basically now the left hand side, where actually instead of platinum I have just Metal mercury, and everything else is center. Okay. Now I am doing the same experiment. One second. What will happen? That's the question. Okay. Now, as I said that okay. Just think about this part. The onset of H plus oxidation. H plus reduction. Okay. That actually happened close to zero. This is basically, let's say, the 0 point. Okay. Zero of potential as well as the zero of current. Okay. And again, as you can see, the basically, so this potential where actually it is like just started overshooting. Okay. So that I can actually call as the open circuit voltage. This voltage, sorry. Okay. Now think about it. Like, what is going to happen? Okay. Now there I gave a logic that it is the H plus reaction, and as I know that with respect to the standard hydrogen electrode, the potential of this guy is always zero, because that was the definition. Okay. Now interestingly, if you do this experiment, okay, keeping actually with the instead of on platinum, if I just do it say on mercury, okay. Oxidation now on say mercury. What you will see is that this thing will come somewhere around -1, okay. And other thing, the reduction will be something around here, close to here. Okay. Now what has happened? Okay, it's the same reaction. Okay, so it's basically H plus is getting reduced, and the other half is basically bromide is getting oxidized. Okay, so now the thing is, whatever you described here, H plus to electron, okay, this is the actual reaction, what is happening, okay. But you defined it with respect to a platinum and hydrogen. That was your standard hydrogen electrode definition. So when you are using platinum as electrode, okay, then the same reaction does not differ too much from the standard hydrogen electrode. That's why around zero it was shooting down. However, when you are using mercury, okay, the potential has changed completely. Okay. So what I'm trying to say here is that just by the reaction, looking at just by the reaction, you cannot say, okay, that reaction, this is the standard reduction potential. You have to always mention, okay, and what condition and using what electrode. Okay. In this case, actually H plus is going to hydrogen, but hydrogen actually we never use as a gas. It is usually absorbed on a metal. Standard thing was platinum, but I showed that the moment I make it mercury, okay, this is very different actually. So which means actually the nature of the interface is extremely important. Okay. Now what is here doing here is that the actual thing is there is a kinetic barrier. Okay, the reaction for the adsorbed hydrogen on mercury surface are much more kinetically inert, and that's why the reaction doesn't happen. Okay. So this is a kinetic inertness of electron transfer at the mercury interface. Okay. Now let us see even more interesting thing. So what I just said is that this entire potential thing, okay, you need to always define basically a particular interface. Otherwise, you cannot like tell anything about it. Okay. Now let us do one more thing. So I had suppose so this was my first experiment, okay, where I did this thing. Second experiment, I basically did the same thing, okay, with mercury. Let me just write it, H plus. Everything else I kept constant. Okay. Now I am making another change. What I am doing is that I am basically adding some trace amount of cadmium ion to it. Okay. What the cadmium ion will do, cadmium itself will create another, like redox couple kind of thing. Okay. So what I am doing, I had mercury. Okay. I had H plus. Okay. In the solution phase, basically I have H plus, I have Br minus 1 molar, and I have suppose cadmium. But cadmium is not of course 1 molar, it is suppose a millimolar range, whatever. Okay. Rest is 7. Rest is 7 means I have Ag here, Ag. Okay. So what I did, I had platinum, I changed it to first mercury. Okay, now I am adding also little bit amount of cadmium. Okay. Now, interesting thing is that I can, apart from these two reactions, I can also have a third reaction, which is something like this. CD equal to plus electron, and then plus. Once this CD is formed, it is basically in presence of the mercury, right? So it basically gets dissolved in the mercury. I mean, it basically forms a nanogroup, okay, the metallic CD. Alright. Now, actually, I will have another redox couple. Okay. So what will happen if I scan now the voltage? I will basically have another onset kind of thing, because I just showed it for two. Okay. Like one reaction, the second reaction, one reaction and the second reaction. But now actually what I am expecting that I will basically have another onset at some point. Okay. And the nature of the part will drastically change. It will be something like, I can send you all the pictures, okay, somewhere. So the actual drawing. So it will be something like this. Okay. And where this is the onset of onset of bromine. Just from so once I have this kind of reaction, okay, like I said that for the first case, okay, I have basically these two reactions, right? Let me actually write all the reactions. So this was for the case number 1. Okay, I had only 2. Okay. Case number 2, when I had the mercury. So this is in platinum. So I still have this reaction, 2H plus 2 electron. Hydrogen, but this hydrogen will be on mercury. Okay. The second reaction is will be something like think about it. Earlier, what I had basically bromine evolution kind of thing at platinum interface, right? I had excess bromide, okay, and that is going as a bromine, right? But in this case, when I change it to mercury, actually it will be Hg2 here. The chemical species is different. So these two reactions are happening. So what I wrote here is not actually the onset of, it's just the same thing. It's onset of Br minus, but here actually it is written as like Hg2 here. As you can see, it is basically the reduction of mercury. Okay. Or if you think in a reverse way, it is basically the oxidation of that. Okay. So this will be actually onset of oxidation of the oxidation of mercury. Okay, clear? Because when I am actually changing the couple, okay, so this actually comes up. Okay. Now you can ask this question: what happened to the other reaction? Does bromine come out? You can actually compare these two. It is basically what I am trying to say is that in the presence of mercury amalgam, okay, I basically have the bromide getting connected to basically mercurous bromide. Clear? Okay. Because the reaction has changed, it's a completely different reaction right now. Okay. And in the third place, I have this thing plus this other reaction which I just wrote, the cadmium reaction. Okay. So here I will basically have onset of mercury oxidation, right? This cut, where actually, as I can see here, okay, where actually I have the onset, okay. This is the onset of the cadmium reaction. Okay. And this is basically the onset of the H plus reaction. Okay. Now you see, this kind of curve actually is known as potential wave. Okay. So I'm actually having a wavy reaction. Okay. Now I actually talked about two different things. One is that I have a discrete potential steps. Okay. Just two couples. Okay. I have basically possibilities of the hydrogen evolution, or I have the possibilities of the bromine oxidation reaction, right? Then I said, moment I switch to mercury, the bromine reaction changes a little bit. I mean, it's a different reaction, okay? And the hydrogen thing actually occurs in a very different potential, okay? Because actually there is a kinetic inertness, okay, which is basically not letting this reaction happen. Plus, I made now the thing even more complicated. I'm saying if I actually add one more thing, okay, what will happen? Okay. So then I'll have actually three kinds of steps, right? Like this, okay. So the long story short, what I'm trying to say here is that if I actually sweep the potential, okay, it will depend on two things: how many species are there, okay, and the second thing is that very explicit nature, okay, of the interface you are using. It can be the same reaction, like the H plus is going to H2, okay, but it depends whether it's a platinum or it's a mercury. Clear? Okay. Now let us just try to rationalize the entire thing. Entire thing rationalization means I actually want a homolumo kind of picture, where I'll start with some potential for the metal, okay, and I'm scanning it, okay, and I know that in the solution I have different species, okay. Each species has a standard reduction potential, okay, and this potential is getting scanned. When actually it will match with one standard potential, okay, I'll have that oxidation, and that's how basically you use in potentiometry. Basically, you have seen this cyclic voltammetry and other things, right? So basically, you sweep the voltage, okay, and monitor the current, and there actually you have an onset of a basically current, okay. When basically this potential is matching, you are scanning the potential or the voltage, okay, and then I have basically multiple like redox species. Now I'll show you one particular diagram here. These numbers you don't need to remember, it's just for your understanding. Okay. Now, what I was showing in that picture, usually the horizontal axis I show the potential. Here actually I am showing the vertical axis as potential, remember that, okay. I am basically scanning the potential as if, right. And again the convention is that the positive potential is at the bottom, the negative is at the top, okay. So if I start with the platinum electrode, okay. And then suppose I have a iron couple, okay. Fe3 plus electron going to Fe2 plus. What is the potential? Plus 0.77. Okay. So it is plus 0.77. Okay. And then around 0. Okay. Of course, I'll have the hydrogen thing. Okay. If I have say 2H plus 2 electron going to H2. Okay. I'm just only writing. See the reduction potential. Okay. And suppose I have in my solution some tin ion, so SN4 plus. So it's basically SN2 plus. The potential is plus 0.15. Okay. And also I have suppose some nickel ion. Ni2 plus 2 electron giving. Okay, that is basically 0.25. And this scale is of course the potential scale versus the standard hydrogen electrode, because that's why the standard hydrogen electrode is 0. Okay. Now if I start with the metal, okay, which is platinum, so the first thing is that what I am starting with, okay, this point, okay, is basically correspond to a voltage where the current is 0. So basically this is the open circuit voltage for a system, okay, where I have one side platinum dipped Okay. Other side some standard electrode. It can be the silver, white, whatever. I don't care because that doesn't change much. And I have different ions. Say I have iron ion, I have tin, I have nickel. Okay. Now what will happen if I just switch the voltage? First, I'll have a rise, okay, due to this couple. Clear? Actually, it's basically coming from the bottom because it's the other hand side, as you can see, right? It is basically the oxidation will happen first. Okay, this kind of curve. Okay. Then I'll have another one, which is due to the tin, which will be close to the 0, 1. Okay, why? Because the standard hydrogen electrode is the 0, 1. Clear? Okay. And then at standard hydrogen electrode, again I will have a rise. Okay. Then it will be flat for some time. Again I will have a rise. Okay, for the nickel. So I'll have a multiple slope. But try drawing this. It is very easy. Like I have already told you. So basically this starts somewhere from here. Okay. As if I'm scanning the potential. Okay. How it will look like. So as you can see that 0 of current, okay, corresponds to here. Okay, what was 0 of current? Current was my y-axis. Okay, so this is 0 of current. Okay, so basically in this case, I'm starting from here already. Okay, 0 of current. I mean, everything will be above it. There is nothing below it. Okay, because I already told you that the platinum's like potential to begin with. Okay, I'm starting from somewhere which is basically corresponding to the 0 of current. Okay. Then this guy will first encounter this thing, oxidation. Okay, so I'll have stepwise rise and all this thing. But I know that when the standard hydrogen thing will go, okay, I'll basically have 0 voltage. So the standard hydrogen onset should be somewhere here. Right? So before that I'll have a rise due to this thing, the tin. Okay. And before that, I'll also have another rise due to the other thing. Okay. So it will have something like this. Okay. And then again it will have something like this. This will be the onset for nickel. So this is nickel. This is basically the hydrogen onset. Okay. This is the tin and this is the iron thing. So that's how I'll see the potential. Okay. So this is a direct kind of correlation. Okay, one-to-one mapping between how I am scanning the potential, okay, of the metal or the electrode solution interface. Again, potential is always acts at an interface. Okay, I am scanning it, but again, always there is another electrode, but we don't care about it because its conditions are not changing during each step of oxidation or reduction. Clear? Okay. Let me give you another example. So this is basically the scale will always be like positive rate will be at the bottom, okay, and negative will always be at the top. Okay, and we are writing everything with respect to the standard hydrogen electrode. Okay. Now what I have here is just only yeah, I have basically the gold electrode. Just one minute, this is 0. The same reaction SN4 plus 2 by 2 SN4 plus that has plus Alright. Now this is very interesting. So this is again with respect to the standard hydrogen electrode. Okay. With respect to standard hydrogen electrode, if you start with a gold, okay, metal, in presence of all these ions, okay, its potential actually starts from here. It's very interesting. Okay. Potential starts from here means actually this is the potential where I am getting zero current. Okay. And then if I actually sweep the voltage to the negative side, I'll see nothing. Okay. In this case, actually, I have to sweep it only to the positive side. It's the other way round. Okay. And then I'll explore all these oxidations actually, because it is reduction equations are written. Okay. But I'll see basically as I move in the positive direction means actually I'm going in the down. Down means actually I'll see the reverse of these reactions. Okay. I'll see all these oxidations happening one after another. Okay. Now, this again does not include the one possibility. This is 0, which is QH plus 2 electron H2. Again, with respect to standard is 0.41. This is chromium minus 0.41, minus 0.76 is zinc. So what I did here, okay, is basically, okay, position of mercury electrode, okay, at 0 current. Okay, now suppose I am sweeping. Now once you sweep this thing, okay, you will find that this reaction, okay, although thermodynamics is suggesting that this should come around 0, it will never come, because actually this is kinetically inert. Okay, and in reality what you will see that this actually comes, I showed you, right, -1 kind of thing. So this actually experimentally will come somewhere here. When I'm scanning this thing, first I will see this thing, second I will see this thing, and then I will see at a very high potential I will see this reaction is happening. Okay, why? Because this reaction is kinetically inert for mercury interface. Clear? So, although thermodynamics is predicting me that these should be the steps, okay, that should occur one after another, okay, there can be actually kinetic inertness which can actually slow down this reaction, and you will see this reaction happening at a much higher potential. Clear? Okay. Now, what it basically means is that the explicit nature of the interface has to be studied. Okay. Now the question is, as I just told you, that there could be a long range where actually I am applying the potential but no current is flowing. Okay. And that basically dictates the polarizability of the metal. Okay. So we have a term here. So it's called ideal polarized or polarizable electrode. What is an ideal polarizable electrode? Ideal polarizable electrode means suppose this is the voltage and this is the current. Okay. So this thing should be very wide. Okay. Over a long range of voltage. Okay. I'm not basically getting trying to, or not being able to strip off or add the electrons. Okay. So that's the kind of ideal polarizable electrode. And there are some examples, so I can just give you. So like if I have mercury plus chloride, again you don't need to remember all these things. Hg2Cl2 plus electron. If I actually take the mercury electrode, okay, it will show around 0.25 volt. And then as a counter electrode, if I add the potassium, so it will show 2.1. Now as you can see that what I did here is that suppose I have a mercury, okay, electrode, and in the solution I have basically potassium chloride. Okay, so there are two possibilities. I can actually form mercurous chloride, okay, which is basically the oxidation of that, okay, or I can actually have reduction of potassium, making the potassium amalgam. Okay, but these two steps happen at a very wide gap. One is happening as 2.1, and sorry, it should be minus 2.1. Okay, and the other one is happening 0.25. Okay, and you have over a very entire long range. Okay, you do not have much change, right? Now, when you do not have much change, what is happening there actually? So, do not have much change in the sense that there is no current flowing. Okay, meaning, as I said, like you can think of that electron pushing and ripping off is basically very difficult. Okay, but inherently, what can happen is that there are surfaces. Okay, there can sometimes you can see a very small current flowing through it. Okay, which is not exactly like sharp rise. It's not an oxidation or reduction. But what I'm trying to say is that this thing, maybe if you can zoom it, maybe you will see slightly slope is there. Okay. Now what happens is that apart from the oxidation and reduction, okay, there are also other processes. What are those processes? Suppose this thing is getting reduced. Okay. Now this thing is in solution. This should first get adsorbed on the metal. Okay. So this adsorption process and all this process also happen, right? So which means for a long time, okay, if you think that there is no charging, things are happening, I'm actually, what is this process? Basically, I'm trying to charge the interface, but it's not charging, okay? Which means the interface is now behaving as a kind of insulator. In a sense, it is, I'm charging something and the charges are getting stored. It is behaving as a capacitor. Okay, like there is a dielectric in between, I have two plates, I'm basically charging. All of you know what is a capacitor, okay. Since this is a dielectric, there is no conductance or there is no electron flow, okay. So the interface is basically behaving as a capacitor, okay. Now there are also these interesting processes when I have the electrons getting transferred. Whenever electrons get transferred, I'll have a current flow, I'll have a spike, okay. These processes are known as Faradic process. You have heard this name, Faradic and non-Faradic processes. Okay, non-Faradic processes are those other processes which are actually happening but not netly contributing to an electron flow. Okay, nevertheless, those are also important. Okay, so which means actually the interface, okay, is not simple like a charge is coming and then just giving its electron. Okay, there are also other steps, and all these steps are happening during this time, but no electron transfer is happening. Okay, which means there is a nice sketch, like I have an electrode here, okay, okay, and then it's not like the simple thing which I was writing, like the ion is coming and then the electron is getting transferred, okay. First it has to come, it has to absorb, and all these things should happen, right? So what means actually at the electrode surface, okay, these processes will happen, okay, in a sequential manner, right? Sequential manner in the sense that I have, suppose, something like, again, this is a very pictorial thing, okay, suppose I have some oxidant, okay, and then I can actually make a reductant, okay. So once I am having oxidant to reductant, I will have basically electron flow, electron going in and out, okay, and this oxidant and reductant are supposed in equilibrium, okay. But what I am saying here, this oxidant, okay, should adsorb on the metal surface as well as desorb, okay. Similarly, this reductant also should adsorb and desorb, okay. And then basically I'll have adsorb oxidant and adsorb reductant, okay. And this is basically free oxidant and free reductant, okay. And this can be actually in the vicinity of the electrode. finally this would also diffuse with the bulk. And oxidant in bulk and reductant in bulk. Okay, so this is actually what is going on. Okay, so there is a region which is close to the electrode, which I can call this region, and then there is a bulk. Okay, so from the bulk actually there is an equilibrium. Okay, which is coming near to the electrode and then getting absorbed, and all these things are happening. After adsorption only I will have the electron transfer. Okay, so when I am talking about say the reduction or oxidation, okay, or basically kinetics of a process, just like I showed that in presence of mercury that reaction is very slow. Okay, so this is not the only factor. All other things will also become very, very important. Okay, for example, this thing is also very important, which is known as mass transfer. Like from bulk, if I have a very ion which is extremely solvated, okay, that ion will move very slowly. Okay, so even if I am actually applying voltage to make this process faster, like more electron transfer, okay, higher current, I may not see it because this mass has not reached here, because it's a very heavy thing. Okay, so all these electrode processes are very much actually inherent to all these individual steps. It is not only these things which we are focusing so much. Clear? Okay. Plus, there can be issues here itself. Like this electron transfer may not be so facile. Okay. There may be some like inherent structure of the surface that is basically preventing the electron transfer to happen. Clear? Usually, this is modeled in a very, very simplistic model, which is known as a double layer model, which is known as electrical double layer model. In the sense that they say that this electrical double layer is what? You basically have a electrode, okay, and then you have ions, okay. Now, what it says is that these ions, some of them are basically very much attached to the electrode. Okay, suppose positive, like it can be positive, it can be negative, whatever it is. Okay. So what I'm trying to say is that suppose the electrode is at that timing is a negative electrode. Okay. So that the positive ions are basically more on the surface of the electrode. Okay. And there are also negative ions which are basically solvated negative ions. Okay. Because once you have excess positive charge, it will attract some of the excess negative charge around it. But these negative ions are not actually sitting on the electrode. Why? Because they cannot sit on the electrode, because the electrode is already slightly negative. If I have a positive electrode, only the plus minus sign will reverse. Okay. And then of course there is bulk, where actually I have solvated negative ion as well as solvated positive ion. Clear? Okay. These two things is known as basically electrical double layer. So, which was proposed by Helmholtz. Okay. He said that usually very much nature, okay, if I just if I just draw a line here and I ask this question, what is the potential? How it is changing? If I just cross this interface, okay. So electrode to solution, if I just go, one can think that okay, there is a sudden jump in potential. It can either increase or it can decrease, depending on whether this has a positive potential or it has a negative potential. Okay, in the way I have drawn it, it's a basically negative potential with respect to the solution. So the potential is jumping. But Helmholtz said no, actually it doesn't happen in a strict jump like this. It will have a smooth rise. Okay. And in this smooth rise, what I will see here, I'll have a region. Okay, before reaching the bulk. In the bulk, if I move and say charge, electron, that experiences no change in potential once it has reached the bulk limit. Okay. How do you measure potential? You basically use a unit positive test charge, okay, and you just move it. If I move it within the metal also, it is kind of uniform potential. That's why I have a flat line here. But the question is how it is changing in between. Then Helmholtz said that actually it doesn't change in a jump. Okay. It basically changes gradually, where actually I have a region, okay, which is known as basically electrode bulk interface. But this region is not like infinitely thin. Something like we were also discussing when we were discussing the surface tension, right? So we said that okay, so there is a excess thing which will be present if you remember, right? It is not like a step function like this. Okay, similar concept. But he said that this thing you can actually think about composed of two different layers. One is if the electrode is negative to begin with, okay, I'll have an excess positive charge kind of layer, okay, and then immediately around it, due to electrostatic attraction, I'll have an excess negative charge kind of layer, and then there will be bulk where positive and negative are all random. Okay, so the electrode and metal, the metal and the solution interface, okay, there is not just only one potential, there is a double layer potential. This is known as basically electrical double layer. In textbook like Atkins or anything, you will see that they always write it as a IHP and OHP. So it's called inner Helmholtz plane, outer Helmholtz plane. Okay. So this is just a model to understand how basically the potential changes, okay, across as I actually traverse unit, say positive test charge across the interface, okay, from say metal to the solution, okay, how the potential changes. So it's not an abrupt change, there will be at least a double layer, okay, to begin with. Of course there can be multiple layers, but at least the minimal model says that there has to be a double layer, okay. Otherwise you cannot explain many other things. So we'll see actually what are those many other things, okay. And second thing, we'll just conclude here today. And the second thing here is that always remember that there is many processes which are associated for this overall cell reaction. It is not just the electron transfer and the flow of electron. Okay, the guy has to first come from bulk, sit there, getting absorbed. Okay, transfer the electron, get dissolved so that the new ion also can come and sit on it. Okay, so all this individual rate will basically constitute the overall rate. If one of them is sluggish, then the overall rate actually gets slowed down due to the rate, if that is the rate determining step, right? Exactly that is what is happening in the Mercury case. That's why the Mercury, although the standard potential thermodynamics is telling me it should happen around 0, in reality we never see it around 0. Okay, because there is a kinetic inertness. Okay. Alright, so we'll just stop here, and next class we'll just talk more about the thermodynamics of this process.